In this video, we explain the significance of the phase boundaries in phase diagrams and how to determine them. Okay, this is a generic phase diagram in which you can see what phase is stable under any conditions of pressure and temperature. Now, we're going to be concentrating on these phase boundaries. Those phase boundaries, what you have is that there's no one phase that is stable. Instead, you have an equilibrium between two phases. That means that both phases can coexist. We're going to look at each one of these phase boundaries in turn, but our first phase boundary is going to be the one for the liquid gas, right? So notice that in this particular case, what you have is that there will be an equilibrium between the liquid and gas, and we call that generally vaporization or condensation, depending on whether you're crossing the diagram this way or that way. Right, so our question is to understand that line a little bit better and see how we can determine it. This line is often called the line of vapor pressures, or the line of boiling points of a particular pure substance. Right, so let's talk a little bit about the vapor pressure to start with. Okay, to illustrate the concept of the vapor pressure, what I'm going to do is simply draw here a container with a liquid, and this could be any liquid that you want. Could be water, or it could be ethanol, or ether, or doesn't matter really. And what we're going to do is put it in a sealed container, okay, where we can restrict the flow of gases in and out. That will be a closed system, right? So it turns out that naturally, the molecules of the liquid are trying to look for a situation of higher entropy. That means that there's a natural tendency for those liquid molecules to go into the gas phase, right? And a few do. Not all of them do, because those liquid molecules are attracting each other, right? So there's a competition between the gain of entropy in going into the gas phase and the stability afforded by the attractions in the liquid phase, right? So eventually what will happen is that if you let this equilibrate, there's going to be a few molecules that have gone from the liquid into the gas phase, and they remain there. And this is a dynamic process, right? So what happens is that all the time you'll have a few molecules of the gas condensing into the liquid, and a few molecules of the liquid vaporizing into the gas. But at equilibrium, the rates of those two processes are equal, and you get to an equilibrium. All right, so the vapor pressure is simply the pressure of the gas molecules that are at equilibrium with that liquid under those conditions. Obviously, that vapor pressure depends on temperature, right? If you now decided to elevate the temperature of that liquid, what you would then see is that, well, those liquid molecules are gaining a larger amount of thermal motion, and that means that more molecules can go into the gas phase, right? So the idea then is that if you were able to plot what the vapor pressure of that liquid is as a function of temperature, it would be something like this, right? It would increase, the vapor pressure would increase with temperature. Well, that is exactly what this line in the phase diagram is, right? So you have the idea there that the vapor pressure of a liquid increases with temperature according to this fashion. There's some curvature to this line that I'm not explaining here in this graph, and that's something that we will see later on in other videos. Okay, but that's kind of the idea in this phase boundary. Now, this line is also the line of boiling points. Okay, so let's try to explain that a little bit better. Right, generally we think that liquids only boil at one particular temperature, but that is actually not true. Okay, so for example, when we think about water, we say, well, water boils at 100 Celsius, and water never boils at room temperature. And as a matter of fact, that is just not true. What happens at boiling is that the vapor pressure of the liquid equals the external pressure. Okay, so if this was the diagram for water, where you have here that vapor pressure as a function of temperature, what happens here is that the vapor pressure eventually gets so large that 100 Celsius, that I'm going to draw right here, right, that vapor pressure equals exactly the atmospheric pressure, which is going to be 1 atm or 760 torr and so forth. Okay, and that's when we see boiling, right? So the idea is that, well, generally when the external pressure is higher than vapor pressure, then molecules from the liquid can only escape from the surface. But if you actually have that the vapor pressure in the liquid is equal to the atmospheric pressure, then as a matter of fact what happens is that the gas molecules will not escape only from the surface. You can actually have bubbles of gas forming anywhere in the liquid, right, if the pressures are the same, and that's when you see boiling. Right, again, the idea then is that boiling requires an equivalency or an equality between the external pressure and the vapor pressure of the liquid, right? So that's why when under normal circumstances for water, we only observe water boiling at 100 Celsius. However, if you were able to change the external pressure on which that water is, you would see boiling at different temperatures. As a matter of fact, if you were to apply a vacuum, right, where the external pressure is much lower than 1 atmosphere, right, so you apply that vacuum, what happens then is that maybe you can now observe boiling at this temperature, right? If your external pressure is equal to that particular pressure, well, this temperature, which might be maybe 50 Celsius, would be enough for the vapor pressure of this water to be equal to the external pressure, and then you would see boiling, right? And you actually can have water boil at room temperature if the pressure is low enough, and that's an experiment that can be done relatively quickly. Okay, so again, yes, this line is the line of vapor pressures where you have that equilibrium between the liquid and the gas. It's also the line of boiling points, but again, this requires that the external pressure be equal to the vapor pressure of the gas. Well, great. So this is the liquid to gas phase boundary. Now, how do you determine this? It turns out that the only thing that you have to do is simply measure these vapor pressures as a function of temperature. That's how you determine that. A very similar recipe could be used to determine this phase boundary. Now, notice that this phase boundary now would be the vapor pressure of the solid or the line of sublimation points. Okay, so the same experiments would take place, but in this case you would not have a liquid there, you would have a solid. Okay, so then the last line that we have to talk about is the line of the solid to liquid phase transition, okay, or equilibrium. And this is going to be the line of freezing points that I'm going to try to write here like this. That is the line of freezing points. Okay, great. Freezing. Okay. Right, so much as what we said with vaporization, that you can get boiling of water at 100 Celsius if the external pressure is 1 atmosphere, and you can change that boiling point depending on the external pressure, the same thing happens to the freezing point, right? So here, what you see is that if you are at maybe 1 atmosphere of pressure, which will be this point, right? This is what we call the normal freezing point. T sub F normal. But as we have learned in other videos, you can change the freezing point with pressure. For this particular substance, if you were to increase the pressure, maybe double it to 2 atmospheres, what you will actually have is that the freezing point has gone up a little bit, right? Again, notice that not all of the substances have this slope be positive as this one, and we just see that the freezing point increases with increasing pressures. Water, for example, has a slightly negative slope in this phase boundary, and what that means is that when you increase the pressure on water, it freezes at lower temperatures, and again, that is just an anomaly. Okay, so how do you then determine this equilibrium phase boundary between the solid and the liquid? Well, the only thing that you have to do then is seeing what is the freezing point of a liquid when you apply different pressures, right? So you would have a liquid at a particular pressure start to cool down, and then whenever you see the solid forming, you would say, well, that's the freezing point. You simply have to repeat that at various pressures to map this line of freezing points. Okay, so in summary, what we've done in this video is describe the phase boundaries between the phases of a phase diagram. And those are the lines where you have an equivalency between the molar Gibbs energies, and you have that phases coexist. In the next video, we're going to talk about the characteristic points where you have here, that's the triple point, and that's what we call the supercritical point.